Hi, I'm Craig Putnam from the WPI Robotics Engineering Program. This is the fourth in a series of videos that we're doing on op-amps. In our last video, we went through in detail the derivation of the gain equation for the inverting op-amp configuration. In this video, we're going to go through the same derivation for the non-inverting op-amp configuration. We'll use the same tools that we used the last time, KVL, KCL, Ohm's law, some algebra, and in the end we'll have the gain equation for the non-inverting op-amp. After we go through this derivation, then we'll do another video where I'll show you some examples of how we actually can use these in a practical sense. Just as a quick review, we're going to be using our ideal op-amp model. The model assumes that we have an infinite input resistance and essentially no current flowing into the input terminals, and that the voltage across those two terminals will be identical, and that we have essentially a zero output resistance from our op-amp. As a reminder, these last two conditions are called the summing point constraints. Again, real op-amps don't behave exactly this way, but the model is actually pretty close, and so we can use that effectively and get good results. With these understandings in mind, let's revisit the non-inverting op-amp circuit we saw previously. If you recall, in that video, I simply gave you the following equation for the gain of this circuit. Now we're going to derive that equation. As before, we'll be using Kirchhoff's laws, Ohm's law, and some algebra, and our ideal op-amp model. We begin by noting that, as was the case for the inverting configuration, there is a feedback resistor, R sub F, connecting the output to the inverting input terminal. There's also a load resistor, R sub L, connected to the op-amp's output. That's where the similarities end. The voltage source, in this case, is connected directly to the non-inverting input. And the other resistor is connected in such a fashion as to create what appears to be a voltage divider. Note first that, due to the summing point constraints, the node where the resistors R sub F and R sub N connect with the inverting input terminal will be at the voltage V sub in. This means that the same voltage, V sub in, is the voltage drop across the resistor R sub in. We also know that no current will flow from that junction between the two resistors into or out of the inverting input of the op-amp. That means the resistors R sub F and R sub in do indeed form a proper voltage divider, and as a result, we can write the following equation. Taking this one last step, we can use this result to calculate the gain of the circuit, and we get this equation. And as you'll note, that's the equation you were provided in the earlier video for this particular configuration of op-amp. By now, you should have a pretty good understanding for how op-amps work, particularly in the closed-loop configuration. In the next video, we're going to explore some applications of op-amps and see how we can use them in real situations.